In the previous video, we introduced affine term structure models. These are models where the short rate has dynamics where the drift and the volatility squared both are affine functions of R. Recall that alpha, beta, gamma and delta here are deterministic continuous functions. In that case, it can be shown that the zero coupon bond prices take the following form, where capital A and capital B are also deterministic functions, which are solutions to the following sets of ordinary differential equations. In this video, we'll have a look at several examples of affine term structure models, starting with the oldest, the Vasicek model. We can write the Vasicek model in the following form, where A, B, and sigma are constant. This is of the form dr is equal to alpha r plus beta dt plus square root gamma r plus delta dwt, where alpha is equal to minus a, beta is equal to b, gamma is equal to 0, and delta is equal to sigma squared, all constant. Note that here the drift is an affine function of r, and that the volatility squared, i.e. gamma r plus delta, is an affine function of r. Now the ODEs for the affine term structure models are given by the following equations. And if we substitute the values of alpha, beta, gamma and delta into these equations, we obtain the following corresponding system of ODEs for the Vasicek model. Now the ODE for B is simply a first order linear equation. It's even separable and therefore can be solved with an integrating factor e to the minus at to obtain the following solution, as I invite you to verify yourself. Then you can verify by direct integration that A is given as follows. Here this is the partial derivative of A with respect to t, which according to the differential equation for A is just little b times capital B minus a half sigma squared times capital B squared. We've just solved for capital B, namely capital B is equal to this expression over here, which we square here. And now we have a straightforward first year integration problem, which is a little bit tedious, but not at all difficult, and yields the following. Now the Vasicek model is time homogeneous. Intuitively, this means that if S is less than T, then the conditional distribution of RT given Fs may depend on Rs and on T minus S, but not directly on S. The Cox-Ingersoll-Ross model that we will tackle next is also time homogeneous, but the Holy and Hall-White models are time inhomogeneous because of the time dependence of the short rate drift terms. Here are 5 sample paths of the Vasicek model with the following parameters. Notice that the Vasicek model is a Gaussian model and that interest rates can be negative, as they are over here. Further note that because we know capital A and capital B, we also know the zero coupon bond yields for every maturity, and we can therefore draw the corresponding yield curves at each time. And here the yield curves have been drawn at time t is equal to 5. So here we have time. On the other hand, here this is not time, this is actually maturity. So this should be a capital T. And these are the yields for all maturities corresponding to the sample paths of the same colors taken at t is equal to 5, i.e. at this time here. Notice that the Vasicek yield curves tend to be monotone, in other words either increasing or decreasing. It is possible for the Vasicek yield curves to exhibit a slight hump, i.e. an up movement followed with a down movement or vice versa, but the hump can only be very small. Next, let's consider the Cox-Ingersoll-Ross model. Here the risk-neutral dynamics take the following form, where A, B and sigma as well as the initial short rate R0 are strictly positive constants. This is also known as a square root process or a Feller process, and as I have already mentioned, will also play an important role in the Heston stochastic volatility model. In the above formulation, the short rate mean reverts to a level theta equal to B over A. Now note that since the volatility depends on R, in fact that sigma times the square root of RT will go to 0 as RT goes to 0, it turns out that the short rate can never become negative. This is because as R gets close to 0, it will experience an upward drift, but the possible downward move due to the Brownian motion will become smaller and smaller as R gets closer and closer to 0. In fact, there are some conditions, the so-called Feller conditions, which ensure that R cannot even reach 0 and will be strictly positive for all t. Now the CIR model is an affine term structure model where alpha is equal to minus A, beta is equal to B, gamma is equal to sigma squared, and delta is equal to 0. If you then put this into the affine form for bond prices, you can show that the corresponding system of ordinary differential equations is given as follows. Here is the differential equation for B with its terminal condition, and the differential equation for A with its terminal condition. Now the equation for B, a so-called Riccati equation, is a bit difficult to solve, and I will leave it as an exercise because of the presence of this B squared term over here. So in an exercise you will show how to solve this Riccati ODE and you will obtain the following solution. Then A can be obtained as usual by straightforward integration, and the solution can be shown to be the following. If you're not up to actually integrating this expression here, you can simply show that this is the correct solution by differentiating it with respect to little t. Here are 5 sample paths of the Cox-Ingersoll-Ross model. Notice that in this case the short rate never goes negative, even though it can get quite close. The corresponding yield curves taken at t is equal to 5 are shown in the graph on the right, where on this axis here we have maturity rather than elapsed time. Notice that here too the yield curves tend to be monotone, and that it is very difficult for CIR yield curves to exhibit a hump. Next, let's consider the Holy model. Here the risk-neutral short rate dynamics are given as follows. Notice that we have time dependence in the drift term, so this is a time inhomogeneous model, but that the volatility is constant. It's easy to see that this is an affine term structure model with alpha equal to 0, beta equal to theta, gamma equal to 0, and delta equal to sigma squared. If we write zero coupon bond prices in the affine form, then the corresponding system of ordinary differential equations for capital A and capital B are given as follows. Now, the differential equation for B is particularly simple, and together with its terminal condition, it's easy to see that the solution is given by the following expression here. If we substitute this expression into the expression for the partial derivative of A with respect to little t, we obtain the following. And thus we can solve for A simply by integrating. Of course, this integral will depend on our choice of theta, which is model dependent. However, we can now do something that we could not do with the Vasicek or CIR models. Namely, we can determine the function theta t, the drift of the short rate, so as to fit the observed initial term structure of bond prices exactly. Here the star denotes that these are empirically observed prices from the market. Equivalently, we can fit the observed term structure of instantaneous forward rates exactly. Now, since the zero coupon bond prices at time 0 take the following form in an affine term structure model, and since we already know that B0 capital T is just equal to capital T, when we take the logarithm, we obtain the following. Taking the partial derivative with respect to capital T, and then it's negative, we obtain the instantaneous forward rate at time 0 for maturity capital T. If we differentiate this one more time with respect to capital T, then we obtain the following. Now capital T here is arbitrary, and if we rearrange this equation and replace capital T by little t, we get the expression for theta t that we seek. Theta t is the partial derivative of the instantaneous forward rate with respect to the maturity variable evaluated at 0 little t plus sigma squared little t. So it depends on the slope of the instantaneous forward rate curve at time 0. Earlier we showed that capital A is given by the following expression, and thus using our expression for theta that we just derived, we obtain the following. We can simplify this, and I'll leave you to sort out the details. However, note that we use integration by parts to obtain this integral here, which results in the first two terms. And the fact that there's a relationship between the forward rate and the logarithm of the bond rate allows us to use a fundamental theorem of calculus to obtain this term here. Now that we know capital A, and recalling that capital B is just given by capital T minus little t, we have the form for the bond prices in the Ho-Lee model. Note that the price of the capital T bond at time little t depends on the prices of the capital T and little t bond at time 0, as well as the forward rate at time 0. To obtain RT here, the short rate at time t, we write the stochastic differential equation for the Ho-Lee short rate as an integral equation and use our expression for theta to obtain the following. Notice that the short rate is Gaussian, with mean given by f0t plus a half sigma squared t squared, and variance given by sigma squared t. So unlike the Vasicek and Cox-Ingersoll-Ross models, the Ho-Lee model can fit the term structure exactly and will give us analytic bond price formulas. However, this does not necessarily make it a good model. For example, because the short rate is normally distributed, negative rates are possible. It's also easy to see that the mean of RT approaches infinity as t goes to infinity. A straightforward computation will show that if t is strictly greater than 0, then the mean instantaneous forward rate for maturity capital T will approach infinity as capital T goes to infinity. In other words, the instantaneous forward rate curve does not level off. Similarly, it can be shown then that the yield curve is unbounded. All of this is a consequence of the fact that there is no mean reversion in this model and that the mean of RT tends to infinity. Our final example is the Hull-White extended Vasicek model, which has the following risk-neutral short rate dynamics. Notice the time dependence of the parameter B here in the drift, so this is also a time inhomogeneous model. This is an affine term structure model with alpha equal to minus A, beta is equal to B, gamma is equal to 0, and delta is equal to sigma squared. And if we substitute this into the bond pricing equation for affine term structure models, we obtain the same ODE for B as for the Vasicek model, and therefore the same solution as for the Vasicek model. We can then integrate the ODE for A to obtain the following, which will depend on our choice of the function B. However, as for the Ho-Lee model, we can use the observed term structure of bond prices or forward rates to determine the value of B, which makes this model fit the observed term structure exactly. Now some tedious computations, which I'd rather not do here, but you can refer to the notes to see them, will show how to choose BT to fit the initial term structure. In fact, very shortly, when we look at the Heath-Jarrow-Morton framework, we'll see how to fit the Hall-White-Vasicek model to the observed term structure automatically in a much more efficient way. Now that we know B, we can integrate the equation for A and obtain the following expression. And knowing both capital A and capital B will yield the bond prices, as you can verify yourself, where capital B is the same as that for the Vasicek model. So we have obtained analytic bond prices for 4 models: Vasicek, Cox-Ingersoll-Ross, Ho-Lee and Hall-White extended Vasicek. We would also like to have analytic formulas for bond option prices, and we will tackle that in the next video.